place. I mean, some people are heavily exposed to it in high school and some people are not. Some people take an introductory geology class in college, some don't. Some people are enrolled in upper level classes. It's all a variety of interests. So I'm going to start what I consider at square one, although this point is sometimes lost on my introductory students, is that really the planet is trying to tell us something through the rocks that are on top of it. I like this little ironic picture up in the right corner, but it's not true. There are things written in stone, including that, but the chemistry of the rocks themselves is trying to tell us something vital about the way it was formed and the processes that happened after it formed. This is powerful information about our planet's past. So the neat thing about rocks is not all of them, but many of them are hard and durable. You know, your average rock that you pick up is a pretty hard thing, difficult to break. It's refractory, which is a big fancy word for saying it's difficult to heat it up to the point where it'll melt or even lose its chemical information. It'll retain the chemistry it was given initially unless you have some very intense processes to subject to it. And they stick around for a while. We've got rocks on this planet that are 4 billion years old. So we can find examples of our early planet, we can find a lot of examples of our more recent geology events. All of these are nicely preserved in the rocks. I like to think of them as the planet's flight data recorder. We usually think of the flight data recorder after a plane crash, but you should know that that's a useful tool for airline mechanics and maintenance people to look at how their aircraft is doing on a day-to-day basis. This is the same thing. This allows us to look back into our planet's past and see back when the planet was young and how it's developed over time. Things we got to be aware of, though, is where are the rocks? How are they distributed? Have they changed in their position since their original formation? And can we deduce clues or processes that have been imprinted on the rocks that we can then use to tell us something? I have a little asterisk down here to tell you that this actually is part and parcel to exploring other planets. Of course, you can't do field geology yet on other planets. We've done the moon, but it's hard to get up there. We do have a roving field geologist on Mars right now, Curiosity. Actually, we've got 2 that are up and running right now. 2 rovers up and running right now on a sequence of rovers, basically trying to do what we can do more easily on our planet here. Yes?
Real quick, while you mentioned Curiosity, how deep can it extract?
Not very deep. It can take things off the surface. It has some tools to sort of clean off the surface and just look at those surface rocks, but it can't go deep into the earth. It can't take big samples away from Mars. But what it can do is scoop up things and send it through some very sophisticated lab equipment it has on board. So I'm going to talk a little bit about similar lab equipment that I would bring rocks back to, but if you got the money and the resources, you can bring them along with you.
Not to get you off topic too much, but I was just curious if you know, like, how far back could that depth tell you about Mars? Like,
well, Mars hasn't been altered recently. It's a fossil planet for the most part. So when they look at Mars, they're looking at 3.5, 4 billion year old information for the most part. Younger meteorite impacts, some slight modification due to atmospheric disturbances, dust and such, wind blowing. But for the most part, you're looking way back in Mars' past. Earth, on the other hand, has been very dynamic in the last 4 billion years. So we don't get the windows back into our deep past like Mars has because we've obliterated that with active processes. But those processes are interesting and they're actually one of the things I want to talk about today. One of the fundamentals of geology is understanding that we like to put events into time periods and not to go too deep into the nomenclature for this and such. But we have little boxes to say, well, this is a period of time that represents certain conditions on the planet. There are 2 ways to look at this. One is to look at the fossil records, and every one of these boundaries in here relates to a time where we see a great appearance of life forms in the fossil records or a great disappearance. There are markers, there are extinction markers, and proliferation markers depending on where you are. That's the important thing to take away with it, because when you're out in the field and you're looking around and you see a certain number of fossils, say you see some clams and some ammonites and some snails, you pretty much know you're dealing with this part of the time period. So you can use that while you're strolling around the earth to say something about the rocks and what age they're attached to them. Really, we don't have any information about how old they are until we apply some clocks to them, the most common being radiometric dating, the decay of radioactive elements into daughter isotopic products. like this particular scheme, using uranium and lead. Uranium, all isotopes of uranium are going away, and they become lead over time. If you keep track of how much lead you generated by the process of this breakdown, you have a very robust clock to get you some of the numbers you see there. We call using fossils and other deluminators relative time because it doesn't really give us a number, and using radiometric clocks absolute time because we do then have a number to hang our hats on there. Mostly what I'll talk about today is the stuff that's relatively new. So you can see Earth history stretches back 4.5 billion years, and really most of the stuff I want to talk about is going to be up here in the last 65 million years, which is just like yesterday geologically. Another fundamental thing about rocks is sedimentary rocks in particular, but rocks on the surface of the Earth are deposited in layers. In other words, they're laid down one on top of each other, making the older stuff on the bottom and younger stuff on the top. So when you're in a place like the Grand Canyon, which is not in West Texas, it's in northern Arizona, but it's a nice layered rock package, so I wanted to show that. And I have this introductory slide to show what the names are attached to each of the units. But each of these represents a certain type of rock that again reflects its origins. For example, this limestone on top, the kaibab, indicates that we had sufficient amount of seawater on top of us to get lots and lots of fossil organisms to form this rock. In fact, this whole package indicates that this part of North America was near or underwater for much of 310 to 250 million years ago. The more important point is that you can get these layers of rock, and it takes hundreds of thousands of years to get each one of these layers. I like volcanoes because they do the same kind of thing much more rapidly. So you might be familiar with volcanic eruptions. This is one style of eruption. This is from Montserrat in September of '96 now. It's been quite a while ago. But this is one of the best pictures I own that is of one of these ash flow deposits, just piles of ash coming out of the volcano. What the ash is just loose little fragments of rock. It was magma that blew out in the air and chilled quickly, and it just streams downhill and it starts forming these layers. This is actually building off a nice peninsula onto the island at that point. You can do this on land, of course, and we can see evidence of that in West Texas as well. This is a stack of 3 of these kind of deposits, one on top of each other. And unlike the Grand Canyon setting, these formed in hours, days, weeks, tops. I mean, each one of these formed almost instantaneously in a geologic blink of the eye. Now there's about 1,000 years or 10,000 years of difference between when this one came out and this one came out. So the timing between eruptions can be quite long, but the deposition of the eruptive products can be quite short. Same layering phenomenon here, oldest on the bottom, intermediate in the middle, youngest on top. So that's powerful information to help us look back into the Earth. Now, if the Earth were not dynamic, all of these products on the surface would probably not be continuing now, but since they are, we know that we have uplift and erosion that's contributing sediments, and we have volcanoes that are contributing new products. But if you let these things sit around in a dynamic environment, they tend to get deformed, upturned, tilted, rotated, even squished in places. So I wanted to show you a slide that indicates this. Again, I'm going far away from West Texas where the rocks are nice and flat to look at this kind of phenomenon. But this is in Utah, north-central Utah, sort of central-eastern Utah, near Moab. This is Canyonlands National Park. This is a series of red sandstones, a thin limestone, some muddy units in between, and they're pretty much flat layered throughout the park. In fact, that's the park's best feature, is these flat layered features that are occasionally weathered into arches and stuff like that. But there are parts of the park where you can see that they're no longer horizontal. And the inference here is that they were horizontal, but the pressure was great enough in the earth as these things were moving around to actually rotate them and do other things to them. As geologists in the field, we're curious about this kind of stuff. Well, how did it get that way if it was all flat? Just to illustrate this point, those two pictures were taken. This is the tilted area and this is the flat area. So a few miles apart. If I had been thinking when I was out there, I should have taken a picture right here, because they're pretty much flat all over until you get to this point, and then they become heavily tilted in sort of this bullseye fashion. So that's the kind of thing we look for in the field, is evidence that something big happened here. Of course, it takes a lot of pressure to move rocks like that, but that would be a curious thing to find out more. So finally, let's go to West Texas. The Trans-Pecos, that's a name, a geographic name we apply to the far netherworld of western Texas, the Big Bend region, and this region up through here going all the way to New Mexico. Basically, we draw the line at about I-10 for really the interesting stuff in Texas, but it does continue on northward from there. And so you can sort of get the geography here. I don't know how many of you have been out this way. It's isolated out there. I've been to Big Bend National Park a couple of times, and one of its virtues is there are very few people out there. So Presidio, Marfa, Alpine, these are not easy to get to towns in Texas. You have to really want to go to. Even though it's kind of convenient to drive out I-10, it goes right through San Antonio all the way up to El Paso. All right, let's put a picture on top of that. Sorry, wrong direction. Of the rocks you can find on top of that map. So this is called a geologic map. It's a spatial representation of the rocks and where their boundaries are. In fact, how far you can watch one unit and then turn into another unit. Some generalities without getting too confused on this map is we're in the same region. Let me back out because I couldn't find a map that had the boundaries clear and the geology. But that's the Rio Grande running through here. A lot of the eastern portion of what's starting the Trans-Pecos, there's the Pecos River there, so it's really this region west of the Pecos River, is still covered by these green rocks. The green are about 60 to 100 million years old, and they're the same rocks you see in central Texas, like in Waco and Austin and the Dallas-Fort Worth area and all over San Antonio. They're white rocks, they're dominated by marine limestone deposits, lots and lots of fossils. So this isn't all that unusual. Where it starts getting weird is you start seeing marine deposits that are older, these blue rocks. And these rocks are actually about the same age as the rocks around Wichita Falls, but they're very different in nature from the rocks around Wichita Falls. And then what I want to focus on today are the orange and yellows in here. These are rocks that are relatively new, in the last 65, 60 million years. These are mostly volcanic. There are some sedimentary rocks in here, but relatively young volcanic rocks that occur over the Trans-Pecos of West Texas, down into Mexico, and we'll leave them and take them up into New Mexico. I have to warn you a little bit about Mexican geology. It's hard to work down there, so our information is better north of the Rio Grande. That doesn't mean there isn't neat things happening in Mexico, they're just harder to see. Black lines on here, these are places where the earth has broken and fragmented, and what we call fault lines. In other words, rocks are moved apart from each other on each of those black lines in a demonstrable fashion. Again, it's the pink and oranges I'm most curious about. If you're wondering what the terrain looks like out there, well, watch the Coen Brothers film, No Country for Old Men, if you can stand sort of its violent pretext. But nonetheless, I think it's about the violence, if I got the point of it correctly. They've shot the whole area in this region of Texas, the Trans-Pecos, and actually this is a stunning shot of the Davis Mountains in the distance and some of the volcanic rocks in the foreground. This is what it looks like today. This is the kind of topography you can see out there. Most of it is in the Chihuahuan Desert, which is the more elevated desert in western North America, has its own flora and fauna, which is, I find, intriguing. But as a geologist, I'm glad it's a desert because that means there are more rocks exposed. My apologies to the botanist. Less, well, I guess you don't want to run into some of the people in this film, but nonetheless, there's fewer interactions with, disturbances from human infrastructure that can be good sometimes. And there's certainly less soil, fewer plants, that means more of the rocks are exposed so you can see them. I find that a beautiful thing, not everybody does. Sorry, question? No question. All right. So, like I said, you could trace this further north. This is the Trans-Pecos. Here's the Rio Grande River and the Big Bend going down there. And we find a slew of these 40 to 25 million year old rocks in the Trans-Pecos. What is really interesting about the Trans-Pecos is the number of volcanoes that are there. Not only is it volcanic rocks, but lots and lots of eruptive centers. But you find eruptive centers throughout western New Mexico and up here to the San Juans of Colorado of about the same age. They overlap in age. And the thinking is now in geology that these are signifying one glorious event. That something big is going on here and basically a north-south trend that starts down in Mexico again, Mexico not as well filled in, and goes all the way up to southern Colorado. And it has to do with the major consequences of building North America as we see it today. That these are signifying one glorious event. That something big is going on here and basically a north-south trend that starts down in Mexico again, Mexico not as well filled in, and goes all the way up to southern Colorado. And it has to do with the major consequences of building North America as we see it today. That these are signifying one glorious event. That something big is going on here, and basically a north-south trend that starts down in Mexico again, Mexico not as well filled in, and goes all the way up to southern Colorado. And it has to do with the major consequences of building North America as we see it today. So the timing is limited to this most recent period of